Alright, in this video we're going to talk about Unit 6, Objective 3, Differentiability. Differentiability is just the function being or having a derivative at a certain point. So if a function is differentiable, then its derivative exists. So just like continuity, we're going to look at places where we are not differentiable. So there's going to be four types of non-differentiability, or 4 points where we're not going to be differentiable. Our first one has, I think, 4 different subtypes, and that's just going to be anywhere where we have a point of discontinuity. So if your function is not continuous, then your function is not going to be differentiable at that point. So we can say that these were holes, vertical asymptotes, jumps, and oscillating function. So if any of those 4 things happen, we're going to say that we are not differentiable. This last one here gets its own number. Even though it's a type of discontinuity, we're also going to say that it is a type of non-differentiability. And once again, we don't really have to worry about those things. So our third one is going to happen when we have a vertical tangent. And if you think about it, differentiable means derivative. Derivative is the slope. So if our tangent line is vertical, that means the slope is undefined. If the slope is undefined, then the function is not differentiable. And then the last one, this is going to be the one that happens more often than not, is when you have a cusp or a corner. They are different things, although if you use just the phrase cusp, you're going to be in okay shape. It's kind of like squares and rectangles. Every corner is a cusp, but not every cusp is a corner. So if you were to just use the word cusp, you should be okay. What these things look like, as far as corners and cusps, are if you have a graph. We'll talk about a cusp first. Kind of comes to a point like a wave. This right here is going to be your cusp. And a corner works the same way, except you have just line segments. So right there would be your corner. Now, why the derivative doesn't exist at these 2 places is going back to our definition of a derivative. So we need to think about limits here. If we take the limit of the slope formula, that's going to give us our derivative. So if we think about taking the limit of the slope formula, so finding the derivative, finding the slope, on the left-hand side of each of these things here, so the slope there and the slope there, we can say that both of those slopes are positive slopes. If we look at the other side, right here and right here, both of those slopes are negative slopes. So remember, we're not talking about the limit of the function in this case, because the limit would be the same. We're thinking about the limit of the slope. We're thinking about the derivative. If I have a positive derivative on one side and a negative derivative on the other side, our derivative itself is not going to exist at that point, because the derivative would have to be the same thing on each side. Now, if you think about a function with a maximum, something that looks like this, you can say that the derivative on the left-hand side of that maximum is positive and on the left-hand side is negative, but you'll notice that it turns into 0, and by it I mean the derivative, right there. We don't have a clear point where our derivative is 0. It's not a nice, smooth curve. So we're looking at that little break, that cusp or that corner, and we're saying we had a positive slope, then a negative slope. So our derivative is not going to exist at that point. So let's look at an example of how AP might ask about this. They would say something like, given f of x is equal to the function 2x minus 3 when x is less than 0, and x minus 3 when x is greater than or equal to 0, they can say, is f of x differentiable at x equals 0? So what we want to think about is the slope on the left-hand side of that line, or I'm sorry, that point, the same as the slope on the right-hand side? So if we think about the derivative, f prime of x, the derivative on the top part is 2, and the derivative on the bottom part is 1. So if our derivatives are not the same thing at x equals 0, then our function is not differentiable. So we have a slope of 2 and a slope of 1. So we're going to say not differentiable. So if we had a slope of 2 followed by a slope of 1, we have a corner right there. And again, if you want to call that a cusp, you could, and AP would be all right with that. So all we need to do is take the derivative of your piecewise function and try to get the derivatives of each piece to match up. The last thing that I want to say, and this goes back to our 4 types of non-differentiabilities. Since we're saying a function that is not continuous, so if there's a point of discontinuity, we're saying that the function is not differentiable. The converse of that would be if a function is differentiable, then it is continuous. And that's going to come in handy when you're looking at free response questions. Oftentimes, AP will tell you that a function is differentiable and then ask you about the intermediate value theorem, and we have to state that the function is continuous. So if they tell you the function is differentiable, they are also telling you that the function is continuous. They are not telling you that the other way around, though. So a function being continuous does not mean that the function is going to be differentiable. Because if we look at this question again, this function is continuous. If you take the limit from the left as x goes to 0, you would get negative 3. If you take the limit from the right as x goes to 0, you'd get negative 3. And the function value at x equals 0 is also negative 3. So that function is continuous, but it's not differentiable. So if you're differentiable, you're continuous. If you're continuous, you are not necessarily differentiable. So we'll call it quits on the video there. We'll see you in the next one.